Hello, good day to you all. First of all, I would like to thank the organizer giving me the opportunity to present my work today. My name is Aravindh Sadhanandham, working as a senior mechanical engineer in Vico Instruments, which is located in California, USA. So it's a semi-capital equipment industry. My part of a job is to design and develop and test these contamination-sensitive systems, optics assemblies. Today, I'm presenting about managing the outgassing risk in the anodized aluminum for these contaminant-sensitive optic systems. So this presentation is totally based on my recent research, which I have done and published about the surface-driven outgassing mechanism in anodized aluminum, specifically in a non-vacuum environment, where I have investigated about the existing researchers about these outgassing types, and based on all the researchers, I have made a framework to control the outgassing risk throughout the production cycle, from raw materials to the end of installation. So, and in this, especially in this sensitive optic systems, even a single trace of a molecule on an optical surface, which will end up to degrade the system performance, even the yield loss on the wafer. Also, the this molecular contaminations can generate a haze formation on the optic surface. It will degrade that optical performance, and it increases scattering, light scattering, and overall it will affect the tool performance, and ended up we have to downgrade the tool. We need to, while fixing this, it takes a lot of energy and cost and tool downtime. So industry is more cautious about while designing this kind of a sensitive optic system. So today I would glad to present this presentation about this key topic. So by stating that, why specifically anodized aluminum taken into the account? Even the system is built up with so many material. So why specifically anodized aluminum? So in optics assemblies, the anodized aluminum is having a lightweight and ease of manufacturing, and even a good thermal properties. So most of the optics assemblies, either it's a stainless steel or on the anodized part, and optic mounts and optic tables or baffles, many components are made up of aluminum. So if the environment is vacuum, so directly the bare aluminums are used. So when it comes to the ambient system, where atmospheric air presence, so using a direct bare aluminum, it having an additional challenge is called as a corrosion, anodized material property having this corrosion thing, and also the color of the aluminum having a higher reflectivity. So using a bare aluminum in ambient system is difficult. So we need a purging and additional environmental controlling design needs to be done, where engineers prefers anodization. So this anodization give you a corrosion resistance, and also for the laser systems, the black anodize help to suppress the stray light, and the durability, surface durability, also good for anodization. So instead of a bare aluminum, anodized aluminum mostly used. But that's again introducing a new challenge, which is anodized surface as a porous oxide layer. It's a honeycomb type porous layer. There is a more chance of volatile elements or like moisture will go and store into that porous surface. Later it get outgas. So that's the challenge. So in this presentation, like how we can retain this anodized aluminum benefits while minimizing this molecular outgassing. So that's the key question which we are trying to address here. So now like we have discussed about the anodized aluminum, like now we can go little deeper into the how the anodized aluminum surface, which I explained about this porous. So let's go to the next slide and take a look at that. So if you see in this slide, the porous, the top layer of that aluminum, anodized aluminum, it looks like that. It's a honeycomb structure. It has a pores and also it has a barrier layer which will build up on the anodization time. This the image looks big, but actually it's very tiny nanopores, which is around like 10 to 30 nanometer of diameter, and there's thickness of that porous layer even like 25 micron thick. So this pore gaps is the place where the chance of moisture and volatile elements or any foreign elements can go and store, and later it get dissolved. That we called as like molecular contamination. So so how this porous oxide is generating, like while in the anodized process, which is showing at the bottom of the slide, where you can, so it starts with the surface preparation and it will go to the anodization. So while the anodization, there are many factors is affecting this porous oxide build. So the temperature and the electrolyte and the voltage and the time duration, how much time we are the anodization is happen, depends on that the porous oxide layer or quality, or like how good that it is. Then once the oxide growth is done, it's going to the rinsing. So after the rinsing, it will go to the main step called as a sealing. That's more important. So the sealing helps to fill those gaps. That's a good step, like we're trying to fill the gaps and seal those gaps to avoid that outgassing. But still, that cannot be able to done at 100%. That's a problem. Like it's very difficult to fill this gap. But sealing also used for to add color. So in this example, you can see that black anodized optic mounts is showing. It's going to the surface preparation and the sealing. So the organic dye or like the black dye added, not only the black, whatever the color needed, it can be added based on the dye. You can get the color, but mostly in the optics mounts or assemblies, like black color used for the optical performance. So once the sealing is done, the pore is completely filled with the dye. Then it will go to the drying stage and it will be go to the packaging. So I have explained here just like anodization steps, which everyone knows about it. So this helps in the later part of the slide how we can mitigate this risk, like this outgassing risk. So now we have understand like how the top surface of the anodization it is, and how the anodization going in step by step. So the now we can move to the next slide and discuss more about how outgassing is happening. So what are the outgassing mechanisms and what are the environmental factors affecting that? So that will give it more idea about like how to mitigate it later part. So I'm moving to the next slide. Okay, so in this slide, um, there are the core mechanism, outgassing mechanisms are grouped into the 4 category. So instead there are many mechanisms. Like I try to give the major mechanism and try to group it into the 4 for a better understanding. So surface adsorption and desorption, then that like only talk about the surface level um, surface level and the molecules on that particular surface to be how it dissolve. Like the the key factor is like how that particle is like connected with the surface, where it go to the thermal activation. So when the system is installed, depends on that thermal temperature and stuff. What are that different gassing mechanism, and the next is the radiation induced. So in semi-capital equipment, semi industries, there are various type of an energy, not only the thermal, like the photon and electron beam machines and photon and the laser annealing machine. There are many various type of system. There is more chances of not only the thermal, and the radiation also can cause the outgassing. And there is the last one which I have explained is the uh, shown here as like a structural, like the surface level, um, based on that structure of that porous oxide layer, and the other than thermal, other than energy, the pressure, and the porous structure. Based on that, how we can uh, group that mechanism. So in this slide, I just showing as 4 group of mechanism, outgassing mechanism. Now we can move on to the next slide and dive deep into that each mechanism, and try to give some visual appearance of, and try to explain this mechanism in upcoming slides. Moving to the in this slide, I've explained that and showing that some visual, as I stated previously, the visual appearance of the 3 different mechanisms. The first one is the surface desorption. So while anodization, or like in a transport or in a storage, there's a chance of the moisture and some volatile elements can be dissolved onto that surface, and due to this humidity and heat, there's a chance of those loosely bound the volatiles can dissolve, and it can affect the optics in the nearby optics which is installed nearby the anodized aluminum. And even the hydrogen also, like while on the rinsing process or in the anodization, there is a hydrogen molecules also will be deposited or like in the anodized surface, and there is a chance of that get outgas due to these environmental factors. So these 2 things called as like, we can call like a bohemite dehydration, where all the water molecules are like dehydrate and create as a haze formation in the optics. If you see in the bottom of the slide, where the clean optics and started to contaminate due to this haze formation, and finally end up like fully covered by the water molecules or like any volatile components, like it will completely affect the performance. So it's stating to that. And the next one is this thermal decomposition. This is quite a little trickier than the other 2 mechanisms, where due to the temperature, there is a possibility of the dye in the seal dye, or due to the temperature, the volatile elements can dissolve and outgas. In addition, while anodizing, to add a color, so then an anodization process, if black color needed for an optics mount or anything, that black dye color pigments may be color pigments added based on the required color, and those organic dyes, due to this temperature, it will start to um, decompose and release the volatile elements. So those elements will affect and contaminate the optics. So that even this issue was investigated a lot, and even NASA identified this one of their research, and started to build some new, instead of an organic dye, they build like a cobalt based dye, which will be withstand more thermal and not to decompose it. So that's one of the risk on using that organic dyes. And this happen on like when the operation is after installing, after when over the period of time, based on that thermal load on the unit which was installed. So these the primary mechanisms where the water molecules and things dissolve and affect the optics, and the organic dyes dissolve and optics. All these molecular contaminations are the key thing, and getting to that, then we can move on to the next mechanisms, quite a little different than this. Moving to the next slide. So far we have discussed the dominant surface and thermal mechanism that are current or normal ambient conditions. Now let's look at to the different mechanisms, which is the first left corner. I have listed the dynamic contamination reservoir. What is about that? So as explained previously, the porous oxide layer can act as a reservoir. Like after the component is installed on the tool or in the system, if that porous oxide layer can absorb that water molecules or any volatiles and dissolve later over the period of time. If the unit is installed on the vacuum system, it's continuously pumped away all the outgassing. But if it is installed on the ambient system, so there is more chance of this outgassing risk. And the lower corner is listed about the pressure driven. It's called as a permeation, whereas the due to this pressure differences, like okay, when the unit is in one particular pressure, all the volatiles are moisture it's inside, and then the outside pressure is differ, so it will permeate through the oxide layer, and it escape and it outgas due to this pressure load. So that's one kind of a mechanism where the molecular contamination happen. And the next one is this energy based radiation and electron induced desorptions, where our tool and semiconductor, different kind of an energy used in a different tool, some laser annealing or like electron beam system. If that unit is an ambient, or if the anodization aluminum is installed, even this photon energy and electron energy can stimulate the surface of the anodized aluminum, and it can dissolve that top surface, and the loosely bound molecules can dissolve and dissolve onto the optics. So not only the thermal, not only the other pressure, even that energy other than the thermal, the photon energy and electron energy, it can dissolve those volatile elements. And the next one is it's a different concept, where the microcrack-induced transport. So the anodized aluminum and the top layer, the aluminum oxide, both are having a different mechanical properties, and especially about the coefficient of thermal expansion. So the aluminum substrate is expanding due to the temperature in a different way, and the top layer, which is the anodized surface, is expanding in a different way. Different way, like due to that difference, there is more chance of the crack start propagate on the surface. Those crack can be giving us a pathway to the dye expose, or the volatile elements can dissolve, and that can go and that can dissolve and contaminate to the optic surface. So uh, this is like it's a different the structural type mechanism. So far we have seen a different kind of outgassing mechanism, starting from this surface desorption, hydrogen, or like even this electron photon and pressure and dynamic, and this micro crack type. So now we can start to think about how we can mitigate this, and how we know these risks are present, and based on that system where it's going to install, and based on the environment, there is more chance of this outgassing, considering all this. So how we can address this issue? So that in the left from upcoming slide, like how we can see how we can mitigate and address this. On this slide, as we see in all the mechanism, so here I've created one framework. So not only the controlling the environment can avoid this risk, so we have to think about the parts in the throughout the product life cycle. So this outgassing risk can be mitigated, and like to improve this anodization surface from the beginning of the part selection, like material selection. So each stages of this part is moving, fabrication to the install and the performance. So each stage, what are the things can engineers can do to improvise this anodized part to address this outgassing? So that's how I'm trying to show this strategies right from the raw material. So when we specify that material, even aluminum typically 6061, or like in a different aluminum grade, not only for the specifying the grade, think about the grain structure. So you mentioned about fine grained aluminum. So the grain structure also play a role on the anodization. So the fine grain anodized aluminum, it will give a more uniform pore. So that will help to reduce this moisture uptake at later part. So while designing itself, the engineer can choose that the fine grained raw material, and moving to that pre-anodization, before anodization, on the finishing stage where the material is chosen and like started to machining it. So on that particular time, try to achieve more surface finish, like at least approximately, like you can say like 4 micron inch micrometer, 0.4 micrometer, or like 16 micron inch. So increasing the surface finish help to achieve a good pore formation. So one of the studies even showing that, like if the surface finish is good, then the moisture uptake to the in the surface is less. So try to achieve good surface finish that can be specified in the drawing itself. So high surface finished part can help to achieve a good pore while anodizing, and even while anodizing, try to control all the so the anodization is more of vendor specific, and but there is a standards, mil spec standards too, to control the anodization, but not all the parameters are specified, like what is the voltage needs to use and what is the temperature time needs to use. Still that can temperature and all the parameters not specified in the spec. It's more of vendor dependent, but controlling that temperature and electrolyte chemistry and the time and the voltage, which will give more uniform pore growth. And so the uniform pore will give good sealing, so that a good sealing will help to reduce the moisture intake or the volatile intake. So that's how we can try to mitigate in the early stage. The sealing is main part where all the pores are sealed in this stage. Typically for adding a color pigment, this sealing is used, but this sealing process helps to close the pore, but achieving 100% sealing, it's a very difficult process. But the majority, like hot water sealing and nickel estate sealing are used, but compared to the hot water sealing, it will introduce the risk of bohemian dehydration. Better to go with the nickel estate sealing, which will help to reduce this haze formation, especially on the optics called like a bohemian dehydration. So prefer a nickel acetate sealing on this 4 stages, where raw material, finishing, and anodizing and nickel acetate sealing. Achieving in that all the criteria helps a lot to get the proper anodized uniform pore surface that helps to reduce the moisture intake or the volatile intake in the later part. By stating that, I'd like to move to the next slide. Post anodization breakout, it's like after sealing, when the part is moved from the anodization. So this process is well known, and industry and mainly aerospace industry prefer this anodization breakout. So this is the key mitigation strategy to reduce the trapped volatile species and moisture from the surface. So after the sealing, due to the transport or due to the handling or even because of that anodization process, there are a chance of the part surface have a moisture and volatile species. This breakout step helps to remove the parts, they remove the moisture and this volatile species from the surface. So the part plays into the oven. So here I'm showing that typical bake-out chamber where the parts will place it and start to bake it at a certain temperature and just certain duration. Due to that heat, all those the volatile species components and the moisture, it will start to outgas, and the surface started to be clean, and it gives more confident and like reduce this outgassing risk. And even previously Ogawa, he demonstrated that this post anodization bakeout can reduce this outgassing risk. He tried to compare this with the multiple samples and proved that this will help to reduce the outgassing risk. And even NASA recommending and many of the aerospace components are bake out this method. So this is one good process, can remove all the VOCs and like moistures from the surfaces and helps to fix the outgassing risk later part. But one downfall is this is not fully standardized so far. What material, what's temperature need to be used, and like what um, uh, duration for that baking. Still, it's not fully standardized, so that's need to be done for like people who are choosing that particular material. It's easy to specify that temperature to get the proper temperature and time to get the proper results. Stating that um, again, like whatever the process we can control, even handling is also an important factor here to avoid this outgassing. Like we always need to use the lint-free wipes to wipe out, and also how we are storing the part. Always try to use that drives place and try to bag it. This is all standard method following by some industries to reduce those contaminant particle on the surface. Even it's more necessary and useful to follow those process. Moving to the next. Okay, so far we have seen what are the outgassing mechanism, what are the engineering strategies from each stage, how we can control the risk to improvise the process. So I would like to give this additional suggestion or like observation where like if even though we have done so all those things, there are some additional options called as an alternative coatings can be used instead of anodized aluminum. Those are like electrolytes nickel plating. Some optic component vendors even use the electrolytes nickel plating. It's a dense coating and it's uniform, and like there is no porosity risk on this electrolytes nickel plating. It's best for precision components. And there is a new thing is a Sogel films where we it's newly developed for this for high temperature applications. It's a dense ceramic coating on top of the aluminum, and also it's good for like UV exposure components and optics. And the actor I think black coating it's called, it's a high very low reflecting. If the power components need to install on that laser, and it's this coating is used, it's no porosity risk and like minimal water release, but it's even for a high temperature. And those Sogel and actor is like it's very less availability, and it's mostly used for this aerospace applications. So these alternative coatings are good, and like there's a trade-off. Like if you want more precise and like it's more expensive, but it give good results compared to the anodized aluminum. So this can also be considered. Depends on that requirement. Moving to the next. So okay, so far we have discussed and what future research can be done. So as we explained in the bakeout section, where the bakeout's temperature, duration, and the setups all are not standardized. It's all vendor dependent now. It's all like experience from the engineers. Like standardization is of the bakeout is more helpful. So it needs to be done so much research and like list the criteria for each material and each grade and each component. It needs to be tested, and like the standard needs to be developed, and even the pore structure, and also how to check the system level, and even for the alternative coating, what is that outgassing value and how can be used against to the anodized aluminum. All those standardization needs to be done. That needed more research and energy and time and cost. Hopefully, like in future engineers and like government will take and start to research. The research community will start to research on this one to address this outgassing risk. Stating that. Okay, now it's a quick recap and what are the engineering takeaway from this presentation. Again, the pore structure is the problem. Like the anodization pore, there is more chance of moisture intake or like the organics will take. So we have to think through about that pore. The pore is a problem, and the key outgassing mitigation thing is that sealing step and the bake out. So those help to reduce this outgassing risk, and not only the thermal and the UV thermal, and those are the two more things can accelerate this outgassing. And we talked about the dense coating, which is an alternate coatings where the nickel acetate or Sogel and ductile coating that can help. It has some trade-offs, and again, like always, how we are handling that parts, that also an important step, where like always try to maintain a dry place and properly vacuum seal that unit. So those all the thing, maybe a takeaway from this presentation. This all helps to reduce this outgassing risk, and it helps a lot to get a better product and a high lifetime optics assemblies, and reduce the cost of ownership and tool downtime, and it will improve the performance too. So that's all I have today. Thank you so much for giving me this opportunity to present my work and observations and about specific to this issue. Once again, thank you to the organization committee, and thank you to the listeners. Thank you.